So the first thing that we're going to talk about today is the nature of light. So is light a wave or a particle? Both, neither, sort of the same thing at the same time. Depends on who you ask. Depends on if you prefer Einstein or Bohr, right? Yep. So we're going to talk about it first in terms of waves in section 1, and then in section 2 we're going to talk about it in terms of particles, and we're going to look at the math behind how we can calculate those different properties. So first, in terms of waves, when we talk about light, generally we're talking about visible light, what we as humans can perceive as visible light. But what that really is part of something called the electromagnetic spectrum. The electromagnetic spectrum is everything from itty-bitty little waves all the way up to really, really huge waves like radio waves. And what we can perceive as light, visible light, is only a very, very tiny section of that electromagnetic spectrum. So when we talk about waves, there are 3 different properties we can measure about a wave. The first one is the wavelength. So wavelength is given the Greek letter lowercase lambda. So this is a lowercase lambda. When I write it, I draw it like that. That's lambda. This is the distance from any point on a wave to the repeating point on the subsequent wave. So from the top of one wave to the top of the other wave, or the bottom of one wave to the bottom of the next wave, or the midpoint of one wave to the midpoint of the next wave. It's the length of the wave. These waves are repeating, so it's the length of basically one repeat unit. Now, wavelength, the units we use depend usually on how big the wave is. If we're talking about radio waves, which are really long, we're usually measuring them in meters. When we're talking about visible light, light waves, those are very, very small wavelengths. We're usually going to report these in terms of nanometers. So a nanometer, NM. What does the prefix nano mean? 10 to the what?
Would that be like -8 or
-9? -9. Think nano 9, 10 to the -9. So a nanometer is 10 to the -9 meters is a nanometer. We're going to need that conversion factor later because, as we see with lots of equations, you need to be able to convert units because oftentimes in our equations we need things to be in SI units. What's the SI unit for length? A meter. And we're going to report it in nanometers, or you will be given it in nanometers. So make sure you know how to convert between nanometers and meters. So that's wavelength. Next, we have something called the frequency. The frequency is not the same thing as speed. Why? Well, because all light is traveling at the same speed, right? At least assuming we're through a vacuum. It's all going at the same speed. So it's not the same thing as speed. That's a common misnomer. Frequency is the number of waves that pass through any given point per second. So it is related to speed, it's dependent on speed, but it is also dependent on wavelength. If you have a larger wavelength, you're going to have fewer wavelengths that can pass through a point at any given second, and so your frequency is going to go down. Frequency is given the Greek letter nu. I know that looks like a V, that is not a V. V is velocity. This is nu. When I write it so that I can tell the difference, I do my V's very small and very straight like that. That is velocity. And then my nu's I curve like that, and that is frequency. Whatever you choose, just make sure that you can tell the difference in your handwriting between velocity, which is speed, and nu, which is frequency, because they are not the same thing. They are related, but they are not the same thing. Now, frequency is how many pass through a point per second. Therefore, it has units of per second. So the unit is per second which can also be written as 1 over a second or second to the negative 1 power. Anybody know what the common name is for a per second? A hertz, good, a hertz, HZ, hertz. That's what the unit is. All right, so we've got wavelength, we've got the frequency. The last thing that we can measure is the amplitude. The amplitude is the height of these peaks. And this tells us the intensity. If we're looking at light, this shows us how bright it is. If we're talking about sound waves, it's talking about how loud it is. Amplitude is the one that we are not going to be dealing with as far as calculating for this chapter. We're going to be focusing on the first two, frequency and wavelength, because amplitude has less effect or tells us less about the electronic structure of the atom that the wavelength and the frequency can tell us, but that's just what the amplitude is. All right, so I said that all light is traveling at the same speed. What speed is light traveling at, assuming a vacuum? We'll round to the 3.00 times 10 to the 8th. So yes, they give it out to lots of significant figures here. We are going to round it, make our lives a lot easier, to 3.00 times 10 to the 8th, and that is meters per second, also known as the speed of light. Speed of light has the symbol lowercase c. What famous equation uses lowercase c? Good, E is equal to mc squared, which we're not going to use in this chapter, but we will use in Chem 152 if you come back later. So speed of light is 3 times 10 to the 8th meters per second, which is really, really fast. So for the purposes of this class, we're going to assume we're always at that speed, always traveling through a vacuum. Of course, light slows down as it goes through different mediums. Slows down in air, slows down in water, slows down going through a crystal, etc. We're just going to assume that we're always in a vacuum to make our lives a lot easier. Now, speed and wavelength can be related using frequency, using this first equation down here. C, the speed of light, which is in units of meters per second, is equal to wavelength times nu, the frequency, and we said the frequency was in 1 over seconds or per seconds, which means what must our unit be here for wavelength? Meters. What unit do you think I'm going to give it to you in? Nanometers, right? So this equation is super easy. The only trick is you have to make sure you're in the right unit. Other than that, easy equation. So let's try this out. Lasers. One type of laser used in the treatment of vascular skin lesion is a neodymium-doped yttrium aluminum garnet. Whew. Tell I've taught this one a few times. Or ND-YAG laser. The wavelength commonly used in these treatments is 532 nanometers. And the question is, what is the frequency of this radiation? Now, sometimes they say the frequency of this light. Sometimes they just say radiation because, again, when we say light, we're usually referring to just the area that we can see. Now, 532 is in the visible spectrum. We can't see that, but the calculations would have been the same if I'd given you something that was much smaller or much larger. So we're just going to use the general term radiation rather than light waves most of the time. But the question is, what is the frequency given the wavelength? So this is our wavelength, and we're asked what is our frequency. So our equation is speed of light is equal to the wavelength times the frequency. So if we rearrange that, the frequency is equal to the speed of light divided by wavelength. But before we can just plug in our numbers, what do we need to do? This is 532. Convert it to meters. Good. So 532 is in nanometers, and again, a nanometer is 10 to the negative 9th meters. So down here, 532 nanometers times 1 times 10 to the negative 9th meters per nanometers. Nanometers cancel, and we're left with 5.32 times 10 to the negative 7th meters as our wavelength. And now we can just plug it into our equation. So speed of light, again, we're just going to use the 3 times 10 to the 8th meters per second divided by our frequency, our wavelength, 5.32 times 10 to the negative 7th meters. What happens to our units? What unit? Meters cancels, and we're left with? Good, 1/2, which is the unit for frequency. All right, now, be careful when you plug this into your calculator, because that times 10 to the -7th needs to be in the denominator. If you're using scientific notation function or calculator, it'll understand that. But if you're actually typing out times 10 to the power, what do you need to do with that denominator? Put it in parentheses. Good. Now, these waves are really, really small, and they're traveling really, really fast. So should the frequency be a very big number or a very small number? Very big number, because if they're really small and they're going really, really fast, you should have a lot of them go by every second, right? So we're expecting a big number here. If you end up with a small number or not really that big and impressive number, that probably means that you forgot to put the denominator in parentheses. So what do we end up getting here? 5.64. Oh, speed of light, yeah. We're just going to round to 3 to the 8th for the purposes. But if you do the exact speed of light, you'll still be within that 2% as far as what Connect wants. Switch here. So I'm getting 5.64 times 10 to the what? Good. 14. Is that a big number? It's a pretty big number. That's how many of these things go by every second. 10 to the 14. That is huge. Big number. So that is our frequency. Any questions about how to convert? I could have asked this in reverse. I could have given you the frequency and asked for wavelength. So be able to not just convert from nanometers to meters, but also from meters back to nanometers. Questions? Good. All right. So what about that electromagnetic spectrum? This image is on page 234, helpful image to have to tell what region of the electromagnetic spectrum you are in, because this is a common question I could ask you. Given the following wavelength or the following frequency, what region of the electromagnetic spectrum are you in? So our electromagnetic spectrums ranges from 10 to the -3rd nanometers all the way up to 10 to the 13 nanometers, which is several meters or several hundred meters long. So everything from itty bitty little gamma rays all the way up to huge radio waves. And in this entire electromagnetic spectrum, the region that we as humans can perceive as visible light is this tiny little slice here, the visible range, which is about from 400 to about 700, varies slightly person to person. It can be down to like 380. It can be up to closer to 750, depending on the person, or a little bit narrower. And then, of course, depending on if you have a color blindness trait, there may be regions of this that you cannot perceive. So 400 nanometers, the smaller wavelength than the visible. This is the high frequency, high energy wavelengths. These are your purples and your violets and blues. Up here, the higher wavelengths. These are your lower energy, low frequency wavelengths. These are your oranges and your reds. Now, I will not ask you specifically, is this green or is this blue, because it gets a little bit iffy where the cutoff is between colors from person to person, but I will ask you which region. Now, if you go smaller than 400 nanometers, so I drop off in this direction, say I'm asking you for 200 nanometers, what is the next region down from visible? Ultraviolet. So if I asked you for 200 nanometers, what region is that? It is ultraviolet. If I go bigger, so bigger than 700, say I've got 800 or 1,000 nanometers, what's the next up region? Infrared. Good, so that's infrared. Those regions are comparatively much larger, as far as how many wavelengths they span compared to the visible spectrum. So in this class, we're mostly going to be focusing on those three regions, the ultraviolet, the visible, and the infrared. But you may have a question that happens to be in the larger areas, the radio waves, the microwaves, or in the smaller areas, the X-rays or the gamma rays. But for the most part, we're going to focus on those three main regions. Yes?
How can we call like the microwaves when they're longer wavelengths?
Because a micro is 10 to the negative 6, while nano is 10 to the negative 9. So a microwave is still larger than a visible wavelength. It's micro because it's 10 to the negative 6. It's just still larger than nano waves. All right. So electromagnetic radiation, as the name implies, has two different components, an electronic component and a magnetic component. These are both waves, and they are overlapped, running perpendicular to one another. So the electronic component and the magnetic component, both the same wavelength, the same frequency, the same amplitude, running at the same speed. They're just running perpendicular to each other. So one of them is the magnetic component, and one of them is the electronic component. So how do we know that light is a wave, or what theory, or what supports the theory? Of course, it's a theory that light is a wave. So this is the most famous experiment that demonstrates or supports the theory that light is a wave. It's called the double slit experiment. So in the double slit experiment, what we have is we have two screens, and we're going to shine light through the first screen, and in that first screen we have a small opening. That small opening then will hit the second screen offset. So if light is a beam, such as we see in the pink one, when it goes through the first one, it will hit this second one and stop, and no light will pass through if light is just a beam of particles. But what is found is that the second screen, which has openings that are offset from the first one, light is able to pass through, which suggests that light is a wave and it's rippling out kind of like ripples in a pond. What's even more interesting is that the light doesn't come straight through the second screen, and a continuous light. What we end up getting over here is regions of light and dark, light and dark, light and dark on the screen right here. So what's happening here is the second screen is letting multiple wavelengths through. It's letting waves through right here, waves through right here, and those waves are overlapping. Now, if I have two waves that overlap in what we call in phase means when one goes up, the other one goes up. So this is wave 1 and wave 2. When we add the waves together, we're going to add the amplitudes. So we add, get a baseline here. We add the two amplitudes, and what we end up with here is very big waves, because we're just adding the amplitudes. So what would that appear like on the screen? Bright light. So that would be like this region, lots of bright light. That's where waves overlapped in phase, so their amplitudes added, and you ended up with this high intensity or high amplitude waves. That ended up as being bright light. What if instead the second wave was out of phase? Out of phase meaning when the first wave was going up, this second wave was going down. They would cancel, and our final wave would be what? Flatline. What would that appear like on our screen? Dark, which is, of course, just the absence of light. So the double slit experiment supports the theory that light is a wave. Because if light was just a beam of particles, you wouldn't get any light on the second screen. And you certainly wouldn't get this banded effect of light and dark, light and dark. Any questions about the double slit experiment? All right, section 2. Quantization. So we talked about converting between wavelength and frequency. Now we're going to take that a step further and talk about energy. So Energy. This is kind of overlapping just a little bit with Chapter 5. Chapter 5 was all about energy in terms of thermodynamics, heat transfer. So the first kind of energy we're going to talk about is black body radiation. Black body radiation is when you heat a solid so much that it stops just releasing that energy as heat, and it doesn't release all of it as heat, and it releases some of it in the form of light. So what is an example of something that as you heat it starts releasing light in your everyday life? Stovetop, right? Stovetop. If you don't have a gas stovetop, those coils, you heat them up and you start seeing that red glow, right? What else? Well, your black body radiation is a solid, not a gas. Yeah. Light bulbs. Now, these are fluorescents, but how do incandescent light bulbs work? No, fluorescents are gas, and neons are gas. A coil. So inside of an incandescent light bulb, you've got a coil. Now, that coil is a filament made out of some sort of metal. As you run electricity through it, you're pumping it full of energy to the point where that coil, that metal coil, will start to give off light. And that's how incandescent light bulbs work. Now, of course, it's highly inefficient because although it does give off some of that energy in light, it also gives off a lot of the energy in terms of what? Heat, which is why incandescent light bulbs get so hot. Any other examples I can think of? What about a toaster? If you look inside of a toaster, you see that red glow. That's another example of black body radiation.
Does it have to be visible light or infrared light?
It can be in the infrared or ultraviolet, yeah.
Our bodies release infrared lights.
Yep. Yep, we do. All right, so studying black body radiation in terms of traditional physics and in traditional idea of wavelengths of light, the math didn't work out. So the person who was working on it was somebody by the name of Planck, and Planck was trying to get the physics to work for explaining black body radiation and the output of wavelengths compared to the energy that was being put into it, and the math didn't add up. So what he ended up doing to make the math work was come up with the idea of quantifying the energy or quantizing it into discrete bundles or packages of energy, saying that you cannot absorb or release energy in fractional amounts. You can only absorb or release energy in these discrete packages. It's like doing a recipe that calls for eggs. If I'm doubling the recipe or quadrupling the recipe or halving the recipe, it's really easy to go from 3 eggs down to 1 egg if you do a third of a recipe. But if the recipe calls for 3 eggs and you want to half it, how hard is it to add 1.5 eggs? Assuming you're not going to cut open the eggs and scramble them up. It's kind of tricky, right? So his idea was that you could only absorb or release heat in these discrete packages. You can multiply it, but you cannot fractionalize these packages. So he gave these packages of energy the term quantum. So a quantum is the smallest unit of energy that can be absorbed or released in the form of electromagnetic radiation. So these are eggs. Can't get any smaller than 1 egg. And he calculated the energy of this as being related to the frequency nu by a constant h. And because he's the one who calculated that constant h, he gave it the name Planck's constant. So Planck's constant is, the value is 6.63 times 10 to the negative 34 joules times seconds. That's a really small number, 10 to the negative 34, really small number. And it's joules times second, not per second. Joules times second. That way, if Planck's constant, h, is in units of joules times seconds, what was the unit for nu, the frequency? Good, 1 over second. So what is our final unit here going to be? Oh, just joules. Because I've got second here and 1 over second, so seconds will cancel. And we'll be left with joules. Is that a unit of energy? Yes, it is. So, given the frequency, pretty easy to calculate the energy, right? What if I asked you go from the wavelength all the way to the frequency or the energy? So here's a question. How much more energy per photon is there in green light with a wavelength of 532 nanometers than in red light with a wavelength of 635 nanometers? Now there's two ways you can go about this. You can do two steps. First of all, take those wavelengths, convert them to frequency using the equation we did in the last section, and then plug that into our equation with Planck's constant. Or you can take those two equations, combine them, and make a new equation that goes directly from wavelength to energy. It's your preference, doesn't really make a difference. Your textbook takes the two-step method, first converting those wavelengths to frequency, and then plugging them into the E is equal to H times new equation. Now, 532 nanometers, that looks really familiar. Why? Yes, the neodymium doped yttrium garnet laser that we just did in the last example. So we've already calculated the wave or the frequency of that. So the frequency of that we calculated in the last problem to be 5.64 times 10 to the 14th. 1 over seconds. So that is our frequency of that wavelength. So how do we turn that into an energy? Multiply it by what? Good, Planck's constant. So using this equation, we take that frequency, we multiply it by H, Planck's constant, 6.63 times 10 to the negative 34 joules times seconds, and that will give us energy. So the energy of the first one, actually, let me do it in green because that is our green light. Woo. Joules times second. Come on, stop it. 14, and that is per second. Running out of space here. So the energy of our red or green wavelength .74 times 10 to the negative 19. Negative 19, and that's in units of joules. So now go ahead and do the same thing for the red light, the 635 nanometers. Convert that to frequency and then convert it to energy. Let's see what you get. And they've gone ahead and converted those nanometers to meters for you. I got 3.13 times 10 to the negative 19 joules. Now both of these are visible light, so we're expecting the energy to at least be somewhat close to each other. They're not going to end up being orders of magnitude apart from each other, so if you got something that's completely different order of magnitude, that means you did something wrong. So a big part of this chapter is being able to recognize what kinds of numbers you're expecting, so that if you get some number that's way out in left field, you know that something went horribly wrong. For example, with frequency, if it's how many pass per second, you're expecting a big number. If you end up with a small number, then you definitely know you did something wrong. Energy, this is the energy of a single wavelength of light, should be a relatively small number. So if you end up with a really big number, probably means you did something wrong. Both of these are visible light, so the numbers should be pretty close to each other. Now, also looking at these, we're starting to get used to these numbers. Wavelengths of things that are in the visible spectrum are about 10 to the negative 7 meters. So if you end up with something that's very different order of magnitude, but you know it's visible light, chances are you need to go back and check your work. The frequencies are in the order of 10 to the 14. The energy is in the order of negative 10 to the negative 19 for visible light. So hugely different numbers, and you know it's visible light should be your hint that something went wrong in the calculations. Now the actual question is how much more? So we're looking for the difference between our green light and our red light. So the last step here is just to subtract the two of those. And so subtract, this was our green versus our red. And that gives us the difference in the energies. So wavelength and energy, directly related or inversely related? Direct means one goes up, the other goes up. Inverse means one goes up, the other one goes down. So as the wavelength got bigger, did the energy get bigger or smaller? Remember, the red light was 635 nanometers, while the green light was the 532 nanometers. Which one has bigger energy, the bigger wavelength or the smaller wavelength? Smaller wavelength has the bigger energy. So are they directly related or inversely related? Inversely. As wavelength goes up, the energy goes, as wavelength goes up, the energy goes down. Bigger wavelengths equals smaller energy. No, frequency is direct, but wavelength is inverse. Yeah. So, which is a bigger wavelength, infrared or ultraviolet? Infrared. So what's higher energy, infrared or ultraviolet? Ultraviolet is higher energy. Good. So again, knowing what kind of numbers to expect, knowing which kind of numbers would be bigger, very helpful in telling you if you're on the right track with these calculations. Well, so far we've had two equations. Not so bad, right? Can handle it? All right. So 5 years after Planck was studying this, or came up with this theory in quantizing energy, this theory was borrowed by another physicist who you've probably never heard of, Albert Einstein. Weird name. It's some German guy. And he borrowed Planck's theory of quantifying energy to explain the phenomenon known as the photoelectric effect. So the photoelectric effect is the idea as you increase the light being shined on a metal, you actually start getting electrons discharged from that metal. So you shine light on a metal and the electrons start getting pulled off the metal and discharged, and we can measure the electrons being pulled off by attracting them to a cathode here. So here's what we have in this instrument. We've got a piece of metal here, and then we've got light being shined on that metal, and then we have a positively charged rod here, a cathode, that will attract any electrons that are released from that metal, and you can measure the electrons pulled off from it by using a voltmeter, measuring any electrons that are coming off of it. What the photoelectric effect, one of the interesting things about this is shining a small amount of light did nothing. There was a minimum amount of light that you had to shine on it before you got any electrons thrown off of the metal. And this was called the threshold frequency, the minimum frequency you had to shine on this metal in order to get any electrons to be pulled off. So Einstein used Planck's idea of quantifying the energy to explain this, saying, well, you can't, until you reach at least one quantum of energy, you're not going to get any electrons. You have to at least meet that minimum before you can get any of the electrons pulled off. Now, wave theory alone cannot explain the photoelectron effect because waves are fractionalized. You can have a fraction of a wave, right? You can get these wavelengths smaller and smaller and smaller and smaller, infinitesimally smaller. So quantifying it doesn't make sense if we're talking about they're being absorbed or released in discrete bundles. That sounds more like a particle. So this was the beginning of the theory that light is a particle, not a wave, or in addition to being a wave, depending on how you perceive the two theories, whether or not they're mutually exclusive or not. So these particles of light were coined the term photons. So using Planck's idea of quantifying the energy, we can quantify the energy of a single photon using the exact same equation. So it looks like a new equation. It's actually the one we just used. It's just instead of the energy of the radiation or the energy of the wavelength, it's the energy of the photon. But it's still the same equation, Planck's constant h times nu the frequency. So what is a new equation is the energy associated with the photoelectric effect. So we know we need to have a certain amount of energy, certain minimum frequency, hitting that metal in order to knock those electrons free. That is called the binding energy. So binding energy is given the symbol W, and this is the amount of energy that it takes to knock an electron loose from the metal. Now, we picture the metal as just a simple atom. So I've got a simple atom, positively charged nucleus. I've got electrons spinning around it here. And I hit this with some wavelength of light. So a wavelength of light, or photons, hits that and knocks the electron free. Now, whatever energy goes into that, how do we calculate the energy of a wavelength of light? What equation? E is equal to h nu, right? Not v, v is velocity, h nu. So this is the energy of the wavelength that hits it. Some of that energy ends up being absorbed by the atom. That's the binding energy. That's how much energy it took to get it to give up its electron. Now, once that electron leaves the orbit of the atom, and this electron goes flying out, what kind of energy does that electron have as it's flying away? Kinetic energy, right? The energy of movement. So this now has kinetic energy, Ke, kinetic energy. So energy, as we learned back in the last chapter, has to be conserved, cannot be created or destroyed. So what we have here is setting the energy that was absorbed equal to the energy that was absorbed from the wavelength equal to the sum of the kinetic energy of that electron and the binding energy that was left with the atom. So that's the new equation here. H nu, which is the energy of the wavelength that hit the metal, is equal to the sum of the kinetic energy of the electron that went flying away, plus the binding energy, the energy that stayed with the atom that it absorbed in exchange for releasing its electrons. This is equation 6.3 on page 239 if you're following along in the book. All right. So in order for these things to be added here, kinetic energy and the binding energy, what's the rule about units when you add things? Got to be the same unit in order to add them, right? So kinetic energy, what unit did we calculate kinetic energy in last time? What? Joules, right? Joules. So we know that h nu is going to give us joules. We just did that. That'll give us joules. Kinetic energy we measure in joules, so we must need the binding energy in joules. I'm not going to give it to you in joules. Binding energy is usually reported in a unit called electron volts, EV, electron volts, or the voltage of an electron. So an electron volt is related to, way back chapter 2, R.A. Millikan's oil drop experiment measuring the charge of an atom. Anybody remember what it was, or the charge of an electron? Right off the top of your head? Should it be a really big number or a really small number? Really tiny, tiny number. So that's what we're going to use to convert between electron volts and joules is that number from R.A. Millikan's oil drop experiment, the charge of an electron. 1 point what?
602.
No, we'll just, it's 2 times 10 to the what? Good. So that's the conversion unit we're going to do between electron volts and joules. It's all coming together. Ready to try this out? All right. So this problem is on page 241, sample problem 6.3, and there's 3 parts to it. First one asks you to calculate the energy in joules of a photon with a wavelength of 5 times 10 to the 4 nanometers, which is in the infrared region. A photon with a wavelength of 52 nanometers, which is in the ultraviolet region. And calculate the kinetic energy of an electron ejected by a photon in part B from a metal with a binding energy of 3.7 electron volts. Now those first 2 problems are exactly the same as the problem we just did, just with different numbers. So we're going to, in the interest of time, go straight to C, which is the only one that's got anything new here. But part A and B will demonstrate what we just talked about the larger the wavelength having lower energy. So you should get lower energy for that infrared photon in part A than you would get for the ultraviolet photon in part B. So let's jump ahead to C. Calculate the kinetic energy of an electron ejected by the photon in part B from a metal with a binding energy of 3.7 electron volts. So our equation from the last slide, H nu is equal to the kinetic energy plus W, the binding energy. So we're being asked to solve for Ke, the kinetic energy. Here. So what are you going to do first here? Good. Convert that 3.7. So that is our binding energy. So that's W. So we want that in joules. So 3.7 electron volts times our conversion factor, 1.602 times 10 to the negative 19 joules per electron volt. And that'll give us it in joules. Should be a tiny number. Getting 5.9 times 10 to the negative 19 joules. So there's W. We got W now. What else do we still need? H nu, V is velocity, H nu. H is Planck's constant. Reminder what that is, 6.63 times 10 to the negative 34 joules times seconds. So we still need nu. What is nu? No. How do we find nu? Nu is the frequency. What's our equation for frequency? It's equal to what? Good. Speed of light divided by wavelength. All right. So we're given the wavelength is 52 nanometers. What do we need to do with that 52 before we plug it in here? Good. Convert to meters. So 52 nanometers is how many meters? 5.2 times 10 to the what? Not negative 7. What? Negative 8. Yeah. Negative 8 meters. That's our wavelength. I'm getting 5.77 times 10 to the what? 15th, good. Again, this is frequency, so I expect it to be a big number. All right. So now we got everything to plug into our equation to solve for kinetic energy? Sure. So let's take this equation, just rearrange it. H nu minus the binding energy is equal to the kinetic energy. And then plug in our numbers. 6.63 times 10 to the negative 34 joules times seconds times the frequency, 5.77 times 10 to the 15 per second, so seconds will cancel, minus the binding energy, which we found to be 5.9 times 10 to the negative 19 joules, gives us a kinetic energy of what? Okay, 3.2 times 10 to the negative 18. I didn't round it all. Well, I used the 3 times 10 to the 8th speed of light. Oh. Careful, because that would be more than 2% off if you have 3.8. All right, any questions on how to calculate the kinetic energy of an electron ejected from a metal? Yes?
Where did the 1.602 times 10?
That is electron volt, or the charge of an electron, from R.A. Millikan's Oladrop experiment in chapter 2. And if you're following along on in the textbook, that is the very bottom of page 239 is where that constant's given. Yay. Ready to move on? All right. So next we're going to talk about, well, why are we talking about light anyways? I thought this was a chemistry class. What does this have to do with atoms and chemicals and electrons and all this mess? So looking at how light interacts with a substance can tell us what's going on down at the subatomic level. What are the electrons doing? So we're going to talk next about something called emission spectra. So emission spectra is as a substance, as a pure substance is going to be have energy put into it, it's going to release light. Same idea as black body radiation. This light is going to have different wavelengths in it. Those wavelengths are going to tell us something about what the electrons are doing. So the line spectrum is the emission of light at only very specific wavelengths. So I'm going to switch now to a demo.